Welcome! In this video, I'll show you how to solve problem 8.14 as it appears in the third edition of Griffiths Introduction to Quantum Mechanics. Now, this problem is very enlightening because it shows us just how powerful the WKB approximation is. Now, we have in the past, in this channel, solved completely the hydrogen atom using the Schrödinger equation. And you saw how difficult that was. It was very annoying. However, we will be able, in this problem, to find the energy levels just like we did in a few videos ago, or more than a few, but using the WKB approximation and much quicker. Of course, there are limitations. We cannot find the wave functions using this method, but if we are simply looking for the energy levels, you will see that our result will be honestly shocking considering how easy it's going to be. Now, what does this problem state? This problem states, use the WKB approximation in this form to estimate the bound state energies for hydrogen. Of course, don't forget about the centrifugal term in the effective potential, and we will have to use this following integral right there. And note that we recover the Bohr levels. Right, and that's what we will show, right? In the case where n is much larger than L and n is much greater than 2, we will indeed get our result back, which is very impressive. Now, keep in mind that the potential in question here is this. It is the effective potential that we saw some time ago when we were solving the hydrogen atom, and it is precisely this, right? Minus E squared over 4 pi epsilon 0 times 1 over r, plus h bar squared over 2m times L plus 1 over r squared. So that is the potential that we'll have to plug into this integral. Now, to begin, as is the case in basically every single WKB problem, we write down our integral and we plug in the momentum, which is 2m or square root of 2m e minus the potential. But the potential is this thing right there. So we get minus this, so we get plus E squared divided by 4 pi epsilon 0 times 1 over r, and then minus h bar squared over 2m times L plus 1 over r squared. So this is the integral that we need to solve. Okay, and let's also be very clear as to what our turning points are. So our turning points, of course, are defined as the points where you evaluate the potential and you get the same value as the energy. So basically, the energy is the same as the potential, evaluated, of course, at R1 or R2. Since there are two cases, let's do this first just in general. So the energy has to be equal to minus E squared 4 pi epsilon 0 divided by R plus h bar squared L plus 1 over 2m r squared. So that is the condition, of course, with r here being R1 or R2, depending on the case. Now, let's go and try to solve this integral. Of course, let's begin by factoring out some constants. So we can factor out the square root of 2me, right? If we write e down here and down here, we can then factor it out. But there is a slight problem, and it is that the 2me, right? This is a negative amount because we are dealing with bound states whose energy is negative. So that means that here we would have the square root of something negative. So we also have to factor out a minus sign just to make sure that everything is okay. Okay, so this is now integral from R1 to R2, with, of course, R1 and R2. We find them by solving this, right? So we find R1 and R2 by solving the equation here. So what we can do is multiply by R squared, put everything to the left side, and divide by E. I guess we can do that. So basically, we get E plus E squared divided by 4 pi epsilon 0, and then minus h bar squared L plus 1 over 2m. This is equal to 0, and we multiply it by r squared, so we have an r here and r squared there. And we could divide by e, but I'll leave that for later. So this here is a quadratic equation that gives us R1 and R2, which are going to be these turning points. Okay, now continuing, here we have this, which is -1, right? Because we factor out this minus sign, don't forget about it. Then we have this amount here, which will be minus e squared over 4 pi epsilon 0 r, and then plus h bar squared. Oh, and we have to add the e here, so 1 over e. And then we have h bar squared l plus 1 divided by, we already had that, 2m e r squared. There we go. Okay, so now what we want to do, because solving this integral is going to be difficult, but thankfully we have here the hint that we were giving. So we want to transform our integral into something that looks like this. Now, first, let's focus on this 1 over x. In our case, of course, it would be 1 over r. That one is relatively easy to get because all we need to do is take the common denominator, right? We can take the common denominator inside of the square root, so square root of, and we have minus r squared, right? And then we have minus e squared divided by 4 pi epsilon 0 e r. And then we have, actually, if we take the square root here, we need to multiply by r, so we end up with this. Okay, there we go. And in this part here, we have plus h bar squared. We don't need to change anything there. So L plus 1 divided by 2me, and all of this is divided by r squared. So this part isn't particularly crazy. All we did was just take the common denominator so that we could then factor out r squared. So we factor it out, we get 1 over r. There we go. Okay, now what comes next? Now we want to change this into something that is basically, as we can see here, x minus a, b minus x. So kind of separating this polynomial into its roots. So we know that any polynomial can be written as the variable, in this case r, minus one of its roots times, and now it depends because it is r minus r2 in the case when this thing here is positive, right? You multiply r and you get positive r squared. But here it is negative, so we actually have to write this as r2 minus r. So basically there's a minus sign difference there. And this is how we can factor, right, any second degree polynomial. If it was a higher degree, you could still multiply by more and more factors, but we only have 2 roots, so this is how we will write it. Now, notice that I used the terms, of course, r1 and r2, and that may look surprising, but the reason for that I will show you right now. If we take a look at the equation that defined our turning points, and we do just some very small changes, so we multiply by -1 and we divide by e, we get minus r squared minus e squared r divided by 4 pi epsilon 0 e plus h bar squared l plus 1 over 2me. We get exactly the same equation that defines the roots of this polynomial inside of the square root. So that means that the turning points that come out of this are going to be exactly the same as the roots of this polynomial. Okay, that's why we went ahead and called the roots r1 and r2. Now, to actually find them, we need to, of course, solve the quadratic equation. But let's make notation a little bit simpler. So what we can do is say, okay, let's define some constant a, which will be minus e squared over 4 pi epsilon 0 e. And why negative? Because this energy here is also negative, and that way we get something positive. Whenever you define a constant, it is better to make sure that it is positive. Otherwise, you have an implicit negative, which is honestly a little bit dangerous. So this thing will be a times r plus, of course, I'm going to get rid of this. It was a little bit too high up. And this thing here is minus b. right? We will define it, we will define b to be minus h bar squared L plus 1 divided by 2me. So this thing here is minus b. Again, why minus? For the same reason. We want b to be positive. Okay, now we want to find the roots of this. So what is R1? What is R2? Well, R1, or rather R1 and 2, they will be both defined by the quadratic formula, which is minus this part, so minus a plus or minus the square root of a squared minus 4 times a and b. So or a and c, but c is minus b. So we get 3 times negative, so it's still negative, and 4b. And we divide by minus 2a, which is minus 1, so it is simply minus 2. Okay, so this gives us R1 and R2. So now we can simply plug our expression, our factorized polynomial. You could go ahead and write the explicit versions of R1 and R2, but it isn't necessary, at least not for now. So square root of R minus R1, R2 minus R dr. Okay, so using this notation, we will see that we have now indeed precisely what is here, so we don't need to worry about solving this integral. We already have the result. So the result is pi over 2. This is pi over 2 times the square root of, I think it was b squared, square root of b minus square root of a squared. I'm going to check because my memory is really not good. Okay, good. And in this case, of course, b and a, they are the roots. So b is R2, a is R1. So now what we need to do is plug it in. And well, of course, this is the result for the integral, but we cannot forget about the constants that we still were carrying around. So minus 2me. Good. Now let's just expand this square. So we get well, all these constants. And then when we square this, we get R2 plus R1, right? They will both be squared. And then we have minus 2 times R1, basically what square root of R1 times the square root of R2. So we need to find each one of these quantities. We need to find R2 and R1, or basically the sum of R2 and R1, and we need to find the square root of their product. So let's begin by finding the sum. So R1 plus R2 means summing this. Now, the plus or minus sign will cancel out. So all we are left with is minus a divided by minus 2 plus, well, this part gets cancelled, so we get plus, and now from R2 we get, again, minus a divided by minus 2, because the only part that's different is the one that cancels out. So here we get a divided by 2 times 2, which is simply a. Okay, so this part right there, this is simply a. Now, what about their product? So what is R1 times R2? And then we'll take the square root. So R1 times R2 gives us, let's see, minus a plus the square root of a squared minus 4b divided by minus 2 times minus a minus the square root of a squared minus 4b, and then we have divided by minus 2. So notice that this is simply, so if we factor out a minus sign, we can put it somewhere over there. This is now positive. And what we have is basically the difference of the squares, right? What we will get here is this thing squared minus this thing squared. And of course, the minus 2 times minus 2, there's no problem. So we get minus, and now we have this thing squared, so a squared minus 4b minus this thing squared, so minus a squared. And all of this divided by 4. So here we get b, right? So this cancels out. We get plus 4b divided by 4, which is b. So the square root of this, of course, is then going to be the square root of b. So square root of b. So this thing right there is square root of b. Okay, and now, well, in principle, we are kind of done, but of course, at least we did the hard part. Now we simply need to plug everything in and start finding the energy levels. So we have square root of minus 2me pi over 2. And what was A? So let's plug in A. A was minus e squared divided by 4 pi epsilon 0 e, right, with the e, yes. And then we have minus 2 times the square root of b, so minus 2 times the square root of minus h bar squared l plus 1 divided by 2me. And all of this has to be equal to n minus 1/2 times h bar pi, right? So that is simply going way, way, way back to this expression. So we plugged that in. Okay, and now we need to solve for the energy. Let's see what's the easiest way of going about this. I would say we just multiply through and then we solve, because when we multiply through, I'm going to change colors. I don't like this one. So when we do that, well, first of all, these pi's will cancel out. That's pretty nice. Then we have a square root of minus 2m. Whoops. And I'm going to make the square root larger because I want to fit in here e, right? Because this e and this e will partially cancel out. And then we have a minus e squared divided by 4, or rather 8 in this case, 8 pi epsilon 0. And so we considered everything there. And then we have minus 2 times the square root. Let's see, now the minus signs that are inside will cancel out. The 2me cancels out. And we are left with h bar squared l plus 1. So of course we can take the h bar outside. So we get 2 h bar square root of l plus 1. And now we have just this thing, so n minus 1/2 h bar. So how do we find the energy? Let's put this to the right side. So we end up with, let's see, n minus 1/2 times h bar. Then we have plus 2h bar square root of l plus 1. And then on the right side, we have this part, which hasn't changed. I simply swapped sides. So we have minus the square root of minus 2m over e. Did we forget about anything? So this is there, that is there. And of course, well, all those constants. So e squared 8 pi epsilon 0. So we want to find the energy, as we know. Thus, let's multiply by the square root of the energy. And then we divide by all of that. So by doing that, we find that the square root of the energy, which or actually, yeah, it's all right. It's all right. We can write it as En if we want, but we can also do it later. It's just nomenclature. It doesn't matter. Okay, and then we have here the square root of minus 2m, a minus sign. We have e squared divided by 2 times 4 pi epsilon 0. I'm writing it like that just to make it a little bit more apparent soon. Then we have this divided by all of those things. So n minus 1/2. I'm going to factor out the h bar. So we have this plus 2 square root of l plus 1. And then we multiply all of this by 1 over h bar. Okay, so this is the square root of the energy. So now we square this and we find, well, this minus sign will become a plus. This square root goes away. Then we have this part squared, and this 2 becomes a 4, right? It becomes a 4, and it will partially cancel out with this 2. So we get 2, and this h bar will be h bar squared. And of course, the denominator will also be squared, but we can't really simplify this much. And now let's call it En, and notice that this thing right there, so this thing there, that's just a constant and not any constant. We know what it is. That is 13.6 electron volt, of course, with the minus signs in front, right? That is what we had found when we are solving the hydrogen atom using the Schrödinger equation some time back. And it's of course what also Bohr found when he did this in this like semi-classical approach. Okay, and then we have still n minus 1/2 plus the square 2 times the square root of L plus 1 squared. So this is our exact results. These are the energy levels using the WKB approximation. However, we still want to check that we actually get the Bohr levels in the case where n is much larger than L and where n is much larger than 1/2. So to do that, let's just go back here. This is very, very quick. And just notice that what we have here, right? If n is much greater than 1/2, then, you know, this doesn't really matter. We can neglect it. And the same with L. Here, this is of order L, right? We get, this is of order L basically, right? The square would cancel out with the square root. So this is much, much smaller than n, so we can neglect it. So we end up with minus 13.6 electron volts divided by n squared, which is precisely what we found in the case of the Bohr levels, right? This, of course, being the ground state energy. So there we go. This is how to solve this problem. As you can see, it is very, very quick. All we had to do was, you know, do a little bit of algebra, but it was simply solving one equation and then, you know, just finding the energy through algebra. So again, the WKB approximation showing us how we can make something as difficult as solving the Schrödinger equation for the hydrogen atom, which we all saw was incredibly, incredibly difficult. This just made us solve it within a matter of, you know, I don't know, just a few minutes. And we got a very, very, very good result. So again, this showing the power of the WKB approximation. So there you have it. I hope that this video was useful to you. If it was, please consider leaving a like on the video, commenting and subscribing, and maybe even checking out my Patreon. So I'll see you in another video. Thank you very much for watching.